All right, this is it. There may be some internet glitches here. Things do not look like they're going smoothly. I am out of options here, but we're going to go forward with this here. This is one of the shorter lectures, so hopefully it won't be too painful. Today we're going to talk about Quicksort. This is one of the high performance sorts that we discussed when we were talking about elementary sorts in the previous lecture. This front graphic is a version of Quicksort in stop time here. So we won't be doing exactly this version, but it's fun to see a graphic. And once you understand one version of Quicksort, it's good to go back and try to look at this picture and see what's going on here. This is a version of Quicksort that works depending on how you have access to elements, but check it out. So we'll start with the basics, explaining what Quicksort is, then we'll do some analysis on the very well understood algorithm. And man, my bit rate is all over the map here. I don't know if this is going to work. All right, that was painful, but looks like we've got things back up and rolling here. All kind of things going wrong on this end technically, but we seem to be back in place. So let's get moving here. Which is, of course, easier said than done. Let's get everybody reset. Anybody want to reset? Ah, yes. Jeez, all right. I think we're in live. Anyone out there can confirm? Can confirm. Anyone? Anyone? Bueller? Aha, there we go. It's running a little. I got some solid green going on with my kbps right now, so I'm feeling pretty happy with it. Made some screen adjustments here. Get myself back into the broadcast. All right, good enough. We talked about Quicksort of the intro, maybe a little jumpy. We'll go back and edit that out a little bit. But today we're going to talk about Quicksort, and today we'll go into, right now we're going to go into the basics, understanding what's going on with the algorithm in general, and then we'll get into some of the analysis on it after that. The problem we had with our simple sorts, and these are our comparison sorts, remember now, we're actually comparing items to items. Our elementary sorts all had the ability to compare every pair of elements. So if you walk into a room with 10 people and none of you know each other, if everyone wants to be introduced to everyone, every pair of people have to shake hands. And this number of handshakes ends up being n times n minus 1, because every one person in the n has to meet n minus 1 other people. But since you don't have to meet each person twice, once for you meeting them and once for them meeting you, we divide that by 2. So we end up with this n times n minus 1 over 2, which gives us our approximately n squared over 2, or the big O of n squared that we get out of all of our elementary sorts. When we do this, we only learn one piece of information per comparison. Take that in contrast to how a binary search works. When I look at that middle item and decide what I'm looking for is less than that item, I can instantly throw away half of the items that I have in my container. So I learn far more than one piece of information with each comparison. That's pretty powerful, and that's what we're going to try to leverage with some of what's going on in Quicksort. The other thing that the simple sorts do is every time they're doing a swap, they're really focused on putting one thing into position. Even in bubble sort, which took the local small and large and swapped them around, the goal there was really to push the smallest thing down to the bottom. The other things getting moved up was just something that had to happen. And as well as in selection sort, we find the smallest item and put it into place, regardless of what else we move or where else we move it to. So we're going to try to attack this problem as well, trying to see if I can move something, move two things at the same time that is going to be a complementary move. So Quicksort ends up being pretty easy to implement. It's very simple in our code. We'll see that in the next slide here. It works really well on a variety of input data, which means things that are already almost sorted, things that are very mixed up. We talk about the number of inversions. Things that are reverse sorted, data that has multiple keys, things like that. So it takes place in place, which means that we don't have to do a full copy of the data. However, it is a recursive algorithm and cannot be made tail recursive. So there's going to be some stack frames depending on how deep we have to go here. So we have to be careful about that when we do our memory analysis. It's time for a lighting update. All right, that's better. Okay, Quicksort is a divide and conquer algorithm. It's going to take the data to be sorted and put it into two separate places that need to be sorted. And there's going to be a division in the middle. We're going to use that to say, well, this is a good place to start. We'll sort that smaller part later, and we'll sort that bigger part as well. So that's what the divide and conquer aspect of it does. And it uses this recursive notion to say, well, I'm sorting this big thing, but that's really just like sorting these two smaller things. And each one of those smaller things is like sorting two other even smaller things. And so that's how it works. But when we get into recursion, of course, we have to have our base case. And the base case in sorting is the trivial one that says an empty list is very well sorted, as is a list with just one item in it. We don't have to do anything to those. So once we get down to a list of size 0 or size 1, that is our base case. We have no more work to do for sorting. We've also got an inductive step, and during that, we're going to find some element and use that to partition the array. So finding the element is one of the things that you can do to sort of flavor your Quicksort. However you find it, however, doesn't matter how you find it, when you get it, you're going to use that element to say, I want everything less than this element over here. I want everything greater than this element over there. And if you're paying close attention, you'll note that if all the things that are less than this item are to its left and all the things that are greater than this item are to its right, then this item must be where it ultimately belongs. So that's one of the powers of partition, which is what we're going to do. Most of the work in Quicksort is done by the partition. So what we do is we form this array that's now left-hand side, all things that are less than the element, and then the element itself, and then the right-hand side. And these are all things that are not less than the element. So that should be greater than or equal to there. Then we can recursively sort those two sides. That's the conquer part. After we've divided it with a partition, then we just conquer it. And that means go back into each one of those and do the same thing again. So here is Quicksort. As I mentioned, it looks pretty simple. We see that we're passing in A, which is my array of data, and I've got a couple of indices that tell me where I start. So I've got this very iterator-like range where I'm going to start and sort some section of the data. We see a constant amount of work here in lines 2 and 3. I see this call to a function called partition in 4, which we'll have to get back at that. And then I've got line 5 and line 6, which are just more calls to Quicksort. So if we're going to perform some sort of complexity analysis here, we're going to have to do something with a recurrence relation. It looks like I can't really tell if this is going to be in the middle without knowing what partition does. And you're not guaranteed that it's going to cut it in half. We're used to things being cut in half when we do this sort of divide and conquer recurse in sort of thing. When we do a binary search, for instance, we cut that right in the middle and then we go into the half that's important. So we don't quite have that luxury with Quicksort. That's where we're at the mercy of the data. But as we look at this partition step, it's going to give us that point, and then we're going to jump into the beginning, or the small part. That's where the data started originally, at left, and go all the way up to, but not including that pivot, right? If we use that same half open interval that we've been using on a regular basis, where it says here ranges from left up to but not including right, when I do this second call in here, my first recursion into the Quicksort, I see that it goes from left all the way up to pivot. But with that pivot being a half open interval, that means that pivot is not included. Okay, no problem. We'll pick that up later. But then as I look at the second call, the second recursive call, I see that that starts at pivot plus 1. So that data item that pivot is the index for is left out of both of these two calls. The first call goes up to but does not include it, and the second call starts right after it. But that's what I alluded to earlier. If I've got all of the small things before this and all of the large things after this, then this is exactly where it belongs. So this partition thing, not only does it find a pivot, but it also puts that pivot where it belongs. So this is not just a read-only step. This is going to make some data change. All right, so looking at it though, it looks fairly simple. Quicksort is a call to this function itself, and I've got a constant amount of work here going on in lines 2 and 3. All I have to worry about then is how does pivot work. My base case in line 2 there, if left plus 1 is greater than or equal to right, that's looking at indices. If these two things are equal, that means I've got an empty range. So if I said left is 0 and right is 0, that would mean that I wouldn't sort anything. And in that case, left plus 1, 0 plus 1 is greater than or equal to 0, so then there's nothing to be done there. If I am trying to sort one item, how would that work? I'd have a left of 0 and a right of 1, because the right would be pointing just past good data, meaning that the data item at index 0 is actually something to be sorted. But if my left is 0 and my right is 1, left plus 1 is 1, and that is equal to right, and so we still can return there. And that's the base case, because we don't need to do any work when we're trying to sort only one item. So that's how this base case works, and that is Quicksort at its high level. What makes it interesting though here is line number 4. Let's look at how this partition is going to work. Ideally, we would love to have the left-hand side and the right-hand side be the same size. I mentioned before, though, we can't necessarily guarantee that, because how do you get the left-hand side and the right-hand side to be the exact same size? Well, if I had the median, half the items would be less than this and half the items would be greater than this. How do I get the median? Well, you sort the items and take the one in the middle. But wait a minute, I'm in the middle of a sort, so I can't necessarily just get this sort of data so that I can sort. It seems like a bit of a waste. And that's what it is. You can't spend the time finding the median because it costs too much. So we'll take a few alternatives. The simplest is to just pick any element. Just like when we do our complexity analysis for average case stuff, we usually say something like n over 2 is how many things I have to look at. N over 2, because sometimes I hit it right in the middle, sometimes I'm way near the front, or sometimes I'm way near the end, but on average, it looks like about n over 2. So what's going on here is as I pick any item at random, it's going to be, on average, equal to the median. Sometimes it will be the median, very rarely. Sometimes it will be less than the median. Sometimes it will be more than the median. But over all of my choices, I will pick something that looks like the median. So that's my justification for just picking any item at random. So what happens is this will, on average, give me something good. I'm not guaranteed to get a good pick. I could actually repeatedly pick really bad pivots. And this is something that can happen. And when that does happen, we'll find that we lose a bit of our, the amazing complexity that we're happy with in Quicksort. So let's take a look at this partition here. A lot to look at. Breathe it in here. There's about 13 good lines of code here. Maybe less, but not much less. So what do we do first? I like to just get right after that complexity analysis. So I look for things like line 2, there's a constant amount of work there, let's ignore that. Line 12 and 13, that's a swap and a return, we can ignore that. Line 2 is just a declaration and an arithmetic operation. So all of the work happens inside this while loop from lines 3 to 11. But the first while loop is a while true, so that one is not one that we've worked on analyzing so far. It's an infinite loop. So we've got to figure out how infinite loop before we can tell how long this loop takes. So it looks like the only way that I exit this while true, this infinite loop in 3, is this break statement right here in line 9. So I can get out when left is greater than or equal to right. So that's the only way that I can get there. As I look at left and right as my input parameters, I think of those as my two indices where I start and end the search. So all I need to know then is how do left and right get updated. I see here in lines 5 and 7, that's where left and right get changed. And it looks like they both live in their own loops. And each one of those loops are pretty basic, but the body of the loop is just a straight increment in 5 or a decrement in 7. So it's a plus plus or a minus minus that those things are getting modified by. So it seems like the left is moving slowly one at a time this way and the right is moving slowly one at a time that way. So when they get to the middle, I will have covered all of the elements. So this is a little bit more difficult to see, but if you go into it, you'll see that this is something that happens linear in the total number of items between left and right. So this while true is my outer loop. This is going to happen linear in n. So looks like partition is a big O of n function. So we've got that going for us. That's our first analysis here as we look at it. Now let's try to figure out what's going on here. I've got this first while loop that says while what's in A at left is less than A at the pivot. So I'm passing in left, and I will be changing left. So that's okay. As I find something on the left that is smaller than the pivot, I want to leave it alone. Remember, after I get this partition done, I want my small things to be left of the pivot and I want my large things to be right of the pivot. So in line 4 here, where I say, if A at left is less than a pivot, I'm okay with that. Leave it alone. Stop looking at it. Plus, plus, left. So we just move on. So I keep moving on as I see things smaller than my pivot until I find something that's not smaller than my pivot. Now I found something in the left-hand side that's big. What do I want to do? I want to swap that out of there. What's a good thing to swap that with, though? A good thing to swap that with is something from the right-hand side that's small. Because the things in the right-hand side are supposed to be large. The things in the left-hand side are supposed to be small. If I can find something small, if I can find something large in the small side and something small on the large side and swap them, then I'll be doing the things that I wasn't getting out of my elementary sorts. Each one of my swaps will be giving me two improvements, right? So that's what we're going to be looking for. That's what this second while loop here does. It starts at the right-hand side, and it starts moving from the right and says, hey, if this value is small, then that's when I want to stop. But as long as I keep seeing big things on the right, I'm okay with that. I'm just going to minus right and move past it. So I've got these two indices that I start with, my left and my right. I'm looking for small things, and as soon as I see a small thing, I keep moving. When I see a big thing, I say, okay, I'm going to swap this big thing. And then I come from the right and say, let's find big things, big things. Oh, there's a small thing. Let's swap those two. And I end up with something big over here and something small over there, and that's exactly how I want it. So, looking closely at this while loop condition, though, there's a few things going on there. While left is less than right. So, as my left index is less than my right index, I may still have some work to do, because you can imagine, once my left index and right index have met, I'm at nothing to do, or if they crossed over, then I definitely have nothing to do. So, that's the first thing that keeps me in that second while. I'm coming from the left until I find something too big, and then I'm going to come from the right until I find something too small or until I meet my too large thing. The second part of that while is and A at right minus 1 is greater than or equal to the pivot. So remember that our right index is never pointing at data that we want to look at. So we have to take that right minus 1 before we use it to dereference that array A there. So A at right minus 1 is the last thing in the range when we start, and it continues to move its way back towards the left as we take away from right. So if we find something that's to the right of the pivot that is greater than or equal to the pivot, that's fine. We just decrement and move past it. All right. So after I get to this, after I've done both of my while loops, I've moved things from the left, I've moved things from the right. If these two are still left and right of each other, then I've got a swap to happen. If they've met or crossed over, then I don't have a swap to happen, I just break out. So if they're still left and right of each other, you'll see that line 10 there calls for that swap. Swap what's at left with what's at right minus 1. So that takes the big thing from the small side and the small thing from the big side and puts them on their proper sides. And then the while loop continues. So we're going to keep going until left and right meet. Somewhere in the middle. It'd be great if it was exactly the middle, but you might understand that if I've got a whole bunch of small things at the beginning, I'm not going to find anything that needs to be swapped out. And that's okay. This is meant to be dealt with that way. So when we get done, the left and right will have met. Line 8, and then we break. We get out of this infinite loop. I've got one last thing to do here. In line 12, it says swap what's in A at left with what is the pivot. So the pivot was declared up here in our first line. It says size T pivot is equal to minus right. What's going on there? That pivot happens to be the rightmost item in the collection. Because remember that as we first pass right in, right is pointing just past my good data. So if I pre-decrement right and set that equal to my pivot index, then when I look there, I will be looking at what appears to me to be the last item in this current range. So that last item in the current range is the one we find the smallers and the biggers for. But once we get done with all of the small things over here and all the big things over there, we still have on the far right that pivot point. So this last line 12 here fixes that. That last line 12 says, when I get done with this while loop, if I swap the pivot from where it was originally found on the farthest right location, if I swap that with where my ultimate left was, where the right and left met, then I end up with something that looks like what I wanted. It puts that pivot right where it belongs. All right, so let's see if we can't run an example of this here. Oh, well, come on back to me. This was great before the lights went out. Now we've got it. Oh boy. Is there? Had this set up and life goes bad. All right, sorry about that. Not my day. This is just definitely not my day. All right. So here's what we got. I'm going to do a partition here. And the first step that we were going to do was to figure out that this is my pivot. So I'll take that. I have no idea what's... Okay. There. Okay. Try this again. I don't know how I jumped out that far slide. Okay. There we go. So we start out our first line here. We pick the pivot. Our pivot location is the last item. So we're looking at 6. We're looking at 6 as our pivot. And as I come from the left-hand side, I'm checking these items one at a time. 2, that's less than 6. I'm perfectly good with moving past that. That's my left plus plus. 9, now this is not less than 6. This looks like a great candidate to swap out of the way. Then I'm going to start from the right-hand side and say, well, how about 8? 8 is greater than 6, so we're fine with that. Let's leave it alone. Now 5, not greater than 6. So this is a small thing on the big side, and I'll be looking at this as left and this is right. And what happens now that I've found 2 of them that are in the wrong place, and since left and right are still distinct, they haven't overlapped, they're not pointing at the same thing, what I'm going to do is swap these 2 things. So this swap is going to bring the 9 over here where the 5 is and the 5 over there where the 9 is, and after that swap my data looks like 2, 5, 3, 4, 7, 9, 8. All right. And I'm just going to leave left and right where they were, so I'm going to continue from where I was, and I say, well, how about 3 coming from the left? Well, that's less than 6. I'm happy with that. 4 coming from the left, that's less than 6. I'm happy with that. 7 coming from the left, that's not less than 6. I'm not happy with that. Well, my right was already pointing at the 9, so then right comes in here, and so I'm at the situation where left and right are pointing at the same thing. So I break out of my outer while loop. The infinite loop gets broken out of. And the last step that I have after that is to swap left with what's in the pivot. And so if I bring this pivot straight down, which is, it's always been there, now my swap goes from this 7 to this 6 there. And I end up with my data looking like 2, 5, 3, 4, 6, 9, 8, 7. And I'm going to draw a box around 6 because 6 is what partition did. 6 is what gets returned, the index of 6. Partition says this is where the partition is, and what that means is this data is not going to be sorted anymore. Remember, the recursive call kind of covers this region, and it also covers this region, because that 6 is going to be there no matter what once I finish this sort. There are 4 things less than a 6, there's 3 things greater than the 6, and the 6 should be right there in position 5 where it is. So this is what happens after my call to partition. Now I've partitioned it, I've divided. All I have to do is conquer over here and conquer over there. I'm going to conquer my left-hand side, conquer my right-hand side by just copying what I did before. On the left-hand side, I'll take this 4 as my new pivot. That's the rightmost thing in this smaller range. I'll look for smaller things. 2 is okay, 5, not okay. That's bigger than 4 from the left. I'm going to have a problem with that. Then I come from the right. I'll say, well, this 3, that's less than the 4 from the right. I'm not okay with that either. Let's swap those 2 things. So we swap them out here. I end up with 2, 3, 5, 4. And then as I move my left there, I find that 5, which is greater than 4. So I'm going to stop moving from the left. And my right is already pointing there, so I don't have any more work to do. This is going to break me out of the infinite loop. And my last step is to trade left with the pivot. And so this 4 and 5 get swapped, and I end up with 2, 3, 4. I'll box that one up again, and 5. So I'll continue recursing down the right-hand side of this. And it looks like we're off the screen. Well, brilliant. This is my day. This is my day. Yeah. Let's clean up a little bit. And I'll redraw what I've got. So after a pass or so, I'll end up with, completely forgot what I just had there. I had something that looks like 2, come on, 2, 3, 4, 5, and that 4 is boxed. 6 is also boxed, and then I had 9, 8, 7. And so this is where my first pivot came in. That's pivot 1. This was pivot 2. And if I continue recursing into the left-hand side, now I'm going to sort this area left of my second pivot. I'll do that by picking this new pivot, the last item in the range. I'll find this 2 less than the 3 from the left, and that's okay. But then my left moves to there, and I'm no longer less than my pivot, so I stop. My right comes in here and says, wait a minute, we've already crossed over. There's nothing to be done here. I end up swapping 3, the pivot, with the left. And since the pivot and the left are the same place, actually, I don't do a whole lot of good work there, but I end up with that 3 exactly where it belongs. And that's what the algorithm thinks. And it knows that the range to the left of the 3, so it kind of looks like this to data, right? I've got a boxed in 3 here. I've got an empty space between 3 and 4 in terms of what the algorithm thinks. That's the right-hand side of the pivot 3. But the right-hand side is of length 0, so that's empty. That's trivially sorted. I don't have to do anything there. I've got the right-hand side of the pivot 4, which is 5. It's of size 1. I don't have to do a whole lot of work there either. But the algorithm doesn't know it's sorted until it jumps in there, right? I've got my pivot 6 here, and then I still have all of my right-hand side from the initial call, which is 9, 8, 7 floating around there. So I'll continue to recurse into my left-hand side. I'll see that this is of size 1, so I don't have to do anything there. I'm going to leave that alone. I'll see this is of size 0. There's nothing to do there. This is of size 1. I don't have to do anything there. And I get back higher level to my very first call of quicksort and then a second recursive call. And now I'm going to sort of quicksort the right-hand side. I'll do that by picking this 7 as my pivot. I'll find this big thing from the left, stop there. I'll look at this 8 from the right. That's okay. I'll find this 9 from the right and say, hey, that's okay. But now that my right and left have crossed, I break out of my while loop and I'm left with swapping these two at the end of things. And I'll have a 7 here, which I can box in. I know it's going to be there forever because that's me putting the pivot where left is. 8 remains untouched and 9 is over there. So here in this case, I've got an empty left-hand side as well because there is a left-hand side of 7 when it's the pivot. It just happens to be of size 0 because it's right next to a previous pivot. So that is a base case call there that I don't actually do any work for. Then I'm going to recurse into the right-hand side there. I'll deal that by picking 9 as my pivot, say that 8's okay, say that 9 is a place where things need to happen, but 9 is also the pivot. So I swap 9 with itself there, and I can leave 9 eternally boxed in. I'll work on 9's left-hand side, which is of size 1, nothing to do there. 9's right-hand side, which is of size 0, nothing to do there. So that's how Quicksort works, by repeatedly calling this partition, finding the pivot, placing the pivot where it belongs, and in the process of placing the pivot where it belongs, it finds everything that belongs to the left of the pivot and puts it over there in whatever order. It doesn't matter. Just as long as it's supposed to be to the left of it, it puts it over there, and everything that should be to the right of it. And so that's where Quicksort gets its speed up. Every time it swaps, it's doing double duty. It's moving a big thing to the from the small side, and moving a small thing from the big side. And that's what's really good about it. All right. Here is another version of partition. So let's take a look at this partition. We'll see that I've got all of the things from the previous version. These slides cut off on this device. I'm going to go back to the other one. I think I'm going to go back to it. Oh boy, there we go. Got it. All right, there's the whole slide. I need a drink. All right, so this partition looks a lot like the previous version of partition, with the exception of the fact that my original partition had a line 2, which these 4 lines have replaced. Everything after line 2 here in the previous version, which is lines 3 through the end, have been completely duplicated here in lines 6 through 17. So the meat of it hasn't changed. All we've done is changed how we choose that initial pivot. Remember, we said it's great to just pick anything at random because it's usually pretty good. That's good when my data is randomly sorted. When I'm taking an average pick, I will get average performance. However, if my data is already mostly sorted, if I keep picking things from the right, they're going to keep belonging way over there to the right. And what that ends up doing is my partition ends up very lopsided. If I keep finding things on the right that belong on the right, I'll have a big left side and a small right side. And so I have to go really deep on my left-hand side because it stays wide. So if I get a good divide and conquer with things in the middle, these two things are even size and I go down a shallow depth there. Whereas if I got a wide one here and a short one on the other side, this is going to go down much deeper as it gets into that recursion. So that's what happens when Quicksort devolves. If I continually pick a bad partition, a bad pivot point, and a bad pivot point is one that leaves a small or empty side, because what happens then is I'm going to do a linear amount of work on each pass, and if I'm only getting one thing correctly placed in a linear pass, then I'm going to have to do this n squared times. So Quicksort on average case and best case is one of our n log n sorts. But when pivots don't go our way, when we get partitions that don't help us, Quicksort can devolve to n squared. We'll check that out in just a minute. But this version of it says, let's say, well, maybe I think that these are kind of already partially sorted. So I can, instead of taking the thing on the right-hand side, what does this do? This takes the item out of the middle. So you're thinking, hey, if this stuff is already sorted or sorted-ish, then if I take something out of the middle, it's going to be median-ish, and that'll be more likely to divide my two partitions into equal halves. So we see here we pick this pivot by taking the item in the middle, left plus right minus left over 2. Right minus left over 2 is half of the items, so left plus half the items is the middle. So this is a way to find the midpoint in an overflow safe calculation. I could just average them, left plus right over 2, but if they were large enough, left and right might cause overflow. So instead of doing that, I'll take left and I'll add half the distance between the two of them, and that gives me the middle. So once I've found that item in the middle, this gets really, really complicated if I want to try to leave it in the middle and then try to pivot around that. So the easy way to do that is find the item in the middle, swap it over to the right-hand side, just like we were used to in the previous version, and then keep going from there as if nothing had ever happened. So we really have just popped these two lines in at the front to say, hey, let's take the item out of the middle, put it at the far right every time that I start a partition, and that way I'm taking something from the central portion of the data as opposed to taking something from one of its extremes. So that's what the goal here is in this version of partition. Other than that, we can see that all of the business of it, all of the loopy action here from 6 on, that's where I get that linear behavior. So this is still linear. I just got a constant amount of additional work that I do at the beginning to say, let's pick something out of the middle instead of something at the end. So here is what it looks like when I try a worst case version of this. If I've got something here that we see this is already sorted, but Quicksort, of course, doesn't know that. If I pick this 5 as my pivot point, I'll come here and say, are you greater than 5? No. No. Ah, here we are. Let's swap 5 with 5. And now I know that 5 is where it belongs, and I still have to work on 1, 2, 3, and 4. So I did, 4 comparisons there. And the next time around, I'm going to say, okay, well, let's take the rightmost item, because this side is now size 0 on the right-hand side. So as I work my way from the left, I'll pick 4 as my pivot and say, that's not greater, not greater, not greater. Oh, 4 is where it belongs. We box the 4 in with an empty right-hand side as well. And I've only got one thing going here. So my pick, because it is repeatedly giving me an empty right-hand side, it doesn't matter if it's right or left-hand side, as long as one of my sides is empty or very small, I end up going quite deep, right? Because the next time through, I'll see that 3 is going to be my pivot, and then 2 and 1 are okay where they are. I'll swap 3 with itself. I've got this empty side over here. I've got some more work to do. Now I'll take 2 as a pivot. And so in this case, I've looked at what? I looked at 4 items in the first loop. I looked at 3 items in the second loop. I looked at 2 items in the third loop. And you see that this is putting me in something that looks like n squared as opposed to something that is n log n. So it doesn't matter if I'm picking the largest or the smallest when I do my pivot. If I pick the largest or the smallest, they're both one of my worst case choices. So as I pick the largest or the smallest, what that does is it leaves my divide and conquer into one big side of size n minus 1, which just ends up being linear work again, and then one empty side of size 0. That's what's going on there. All right. That is the Quicksort basics. It was not easy, but we got it done. Thanks for sticking with me, gang. This has not been a great day. Let's do some analysis. We'll look at the performance of Quicksort and see why we like it so much. First, let's get our time analysis in. The cost of partitioning n elements, we already looked at that in depth. We said, how long does it take me to do that actual infinite while loop? Said because we're just moving the thing from the because we're moving the thing from the left to the right and the thing from the right to the left, and they're going to meet in the middle somewhere in the middle, somewhere inside the boundaries, let's say. Middle makes it sound too good. Because they're going to meet somewhere inside the boundaries there's going to be a linear amount of work. So the cost of partition is always just n, big O of n. It's a linear amount of work. So in the worst case, we talked about the pivot always leaving one side empty. So then when I'm trying to deal with this T of n, my recurrence relation, when I say that doing this work on n items, the time it takes to work on n items is n, of course, that's the linear partition. And then I've got the two sides. One is of size t of n minus 1, and the other is size t0. So t of n equals n plus t of n minus 1. If we say that t of 0 is a constant, then I end up with something that looks like t of n is equal to n plus t of n minus 1 plus c. We can get this one by substitution. We can't use the master theorem on it because we're not dividing there. We can get this by substitution, however, and it looks like, even without a parenthesis there, this is going to be big O of n squared. You can do that with substitution. N squared gets us there. In the best case, I get the pivot dividing the elements evenly, so I still have my linear pass of the partition. That's what the n is here in this second version. And then I've got half of them on the one side and half of them on the other side, so it looks like t of n over 2 on the left, t of n over 2 on the right. I can combine that and say t of n is now n plus 2 times t of n over 2, and this one, of course, does work well with the master theorem. I can also just do this by substitution if I'm feeling algebraic that day. But once I solve this one, I end up with something that looks like t of n is approximately n log n, a big O of n log n. The average case is quite a bit harder to figure out, but the good news is Quicksort is really old and really well understood. And I can tell you magic numbers and really believe them. If you want to figure this out, you should dig deeper into algorithms. But it turns out that the average case is tricky to find, but it's somewhere between 2 times n log n and approximately 1.39 n log n. Not something that you need to know. What's really important is average case, n log n. Best case, n log n. Worst case, n squared. All right, so worst case, Quicksort is just as bad as one of my elementary sorts. But best case and average case, it kicks a whole lot of butt. In terms of memory analysis, was not much in terms of variables. We just had a local swap variable, or maybe a couple of indices that I looked at left and right. But I am making recursive calls. If you remember the very first version of it, where we had our base case, then we did the partition step, then we called Quicksort on the left half and Quicksort on the right half. There's no way to make that Quicksort on the left half tail recursive, because we have to call Quicksort on the right half. So we will have stack space for some portion of this. So it doesn't take a whole lot of memory in the algorithm itself, but its implementation does take memory. That can't just be ignored. We have stack frames to be dealt with. If we've got a lot of data and we end up with something that looks like our worst case scenario, that means we've got a stack frame for every item. This can end up taking a linear amount of memory and a quadratic amount of time. Quicksort can be really bad, but it can be okay, right? Because average case and best case, it's not that bad, and we're more likely to see the average case than we are to see either the best case or the worst case. So the first recursive function can't be tail recursive. It has to have a new stack frame. The second one can be tail recursive. It can reuse the current stack frame. If you would like to be tricky, you can write your Quicksort to say, hey, I've got this partition and it divided it into 15 things over here and 3 things over there. I want to make sure that my recursive call takes the 15 side. You can do that and say, well, if this side is smaller, then make that one be the non-recursive call. make that be the one that does have to, non-tail recursive call. Make that the smaller side take up stack frames, whereas the bigger side every time I'm going to use the same stack frame. So you can sort of reduce the memory impact there. That takes an additional comparison, however, as we look at the two sides and how big they are. All right, so here is just that. What we had in our previous version of Quicksort. We've got our base case. This is how I get out. There's my partition step. And then all I had after that was 2 calls to Quicksort. Now I've got 4 calls to Quicksort. I'm only going to use 2 of them, however. It says if the distance from the pivot to the left, the left-hand side, if that is smaller than the right-hand side, then we're going to use the left-hand side, the small side, as the side that generates new stack frames, and the large side, the right-hand side, as the side that reuses my current stack frame. So I'll tail recurse into the right. If it's the other way around, of course, you see we tail recurse here into the left in line 10. So lines 7 and 10 are where the tail recursion happens, so that's where my savings come from. I'll put the big sides there, and that's an optimization that you can use in Quicksort. What does that mean my worst memory requirement is? Well, also tricky here. But on average, if I'm doing this, it does help me show up a little bit closer to average case there. Something like n over 2 is what my total recursion depth looks like. And that's pretty nice. Because when both sides are equal, I'm only going to go log n deep. And so this back and forthing thing to keep moving towards the tail recursing into the large side is going to get me closer to having that n over 2 depth, log n depth. So the advantages, of course, of Quicksort is it's on average n log n. Best case, n log n. It's got a short inner loop. It's really efficient with memory. And as I mentioned, it's really old, so it's very well analyzed and understood. Quicksort is part of the C library. You just call Qsort. It's a function that does a Quicksort for you. The disadvantages, of course, is the worst case is somewhere out there to be found. So if you are sorting data that's already sorted, well, it might take a whole lot more time than you really needed, right? So n squared time in a worst case, it is not stable. If you think about the way that stability should work, if I find something to the left of something equal to it, it should stay to the left. But I might find that in the wrong place and decide to swap it to the other side without any concerns. And so Quicksort is not stable, and it's not gonna be stable too soon. So don't worry about that. Writing partition is something that you can make a mistake and really flub things with. But other than that, Quicksort's a pretty solid algorithm. That's why it's used in the STL. The Quicksort is what intro sort uses as the workhorse. The thing that does the hard work is Quicksort in the STL, in standard sort and intro sort. So we saw that where the split happens is really what makes or breaks Quicksort. So any single choice could always be the worst one, and since it costs too much to figure out what the best choice is, I'm just gonna try to hope that I get something in the middle. But if I want to go beyond hope, I might say, what if I was gonna try to just nudge it one direction? I could find a way to make sure that there was never an empty side. That's what sampling does. The simple sample says just take 3 items. If I pick 3 items from anywhere in the container, and then I can look at which one of those is in the middle in a constant amount of time. With 3 items, I just have to make a couple of comparisons, and I know which item is in the middle, and then I can say, great, let's use that as my pivot. If I use that as my pivot, I know that I'll have at least one item on both sides. So that's one way to do it. Probably going to give you better performance. Let's see how this might shake out. So here we can do median sampling. This is what it's called. We'll find the median of the first, middle, and last elements in this case. So you think, well, there's usually small things to the left over here. There's usually big things to the right over there, and sort of middle-ish things in the middle. If I take one of each of those and then get the median of them, say, hey, now my pivot is 14, and that's might be better than picking 2, which is on the far right over there. Picking 2 as my median is a lot worse than picking 14 as my median. There's only one item less than 2, so I would have a pretty wide side on one side and a very narrow side approaching my worst case on the left over there. But sampling here, this 14 and 7, I think it splits it up fairly evenly, like a 9 on one side, a 6 on the other, which is pretty nice. So that's one way to do it. You can do it in this positional way. Another way to do it is with random sampling. So this is just finding any 3 elements, and then you find the median of them here. What's picked was 1, 42, and 28. The median of those is just 28. So if we use that as our pivot, we end up with something that's pretty decent. We still end up with, I think, 9 elements to the left of that and 6 elements to the right, which is another decent split there. It's not perfect, but it's a lot closer to n over 2 than something on the far right like that 2 is. So that's another way to do it. And so far we've been talking about sampling 3 items, but you could do any odd number, really. It works great, right? I could take 5 items and find the median of that. Then I'm sure that there's going to be 2 on this side and 2 on that side of my pivot, no matter what. I could pick 7 items. I have 3 over here and 3 over there, no matter what. So that could speed things up. I think one of the STL implementations does a median of medians. And so it finds 3 items, medians them, finds 3 more items, medians them, finds 3 more items, medians them, and then medians all 3 of those items. So we end up with that having sort of like the median of 9, where we've got at least 4 on this side and at least 4 on that side. So that's an interesting way to do it. It might sound like a lot of work, and like, wow, that's a lot of work doing this median thing. But when you're talking large sorts, that is negligible work. So if I'm sorting 100,000 items, taking the time to find the median of 9 of them is nothing. It's just not even recognized in terms of execution time. So you've got that, and if that thing prevents you from going to 100,000 squared, which is where we've got our worst case scenario, we're going n squared. If that keeps me in 100,000 log 100,000, I'm pretty happy with doing it. So sampling is a really powerful technique that can improve things quite a bit. Some other improvements that we can use is that because divide and conquer has to go down to a base case, it has to get down to where we say, well, am I sorting a list of length 0 or a list of length 1? Because that's when I stop. Until I get down there, I don't stop. I got a lot of recursive calls that say, sort this really short region. Sort this really short region. So we could reduce the cost of sorting these small regions. As we remember from our elementary sort day, that insertion sort is the fastest sort for small arrays. So insertion sort is even faster than quicksort when we're talking a small array. So one way to do this is to just bail out. Say, hey, I've got to some small size, so rather than trying to quicksort these 5 items, I'll just insertion sort them. It's faster. I think that the STL implementations commonly used are somewhere around 16 or 32. I think it's less than 15 in the G++ or the new CSTL, as long as you're less than 16. So it's 15 or fewer items. Intro sort doesn't even use quicksort anymore. It uses quicksort when it can, but when it gets down to lists of less than 15, it just uses intro sort. It just uses insertion sort. Here's our summary. On average, we've got this n log n sort. The efficiency, of course, was based upon how we found that pivot and how often we got something near the middle. We could randomly choose that, or we could positionally choose something in the middle, swap it to the end. We looked at sampling multiple keys and finding something that would say, with this as my median, this is my pivot, I'm sure to have at least something on both sides that can keep me from going to my absolute worst case n squared. So there's other creative methods that you can find to improve that pivot, but those are beyond the scope of 281. We're just trying to get a fundamental understanding of quicksort here. There's other methods of tuning. We looked at what happens if I can tail recurse into the large side. We looked at talking about using insertion sort when we get down to a small enough size. There's 3-way partitioning. There's a bunch of other things. There's another really great CS page in Wikipedia. Go read it, spend some time there. Lots of fun. All right, that's my analysis of this. And after this, we're going to just give us this is the end of our talking about sorting, including yesterday's version of elementary sorts and today's version of quicksorts. Oh, I take that back. We've got one more sort after this, right? we've got merge sort. That'll be next week. So my elementary sorts are up here: bubble, insertion, and selection. Those were all worst case n squared. We've talked about heap sort. Heap sort, remember, that was we were required to take the data and then heapify it first. That was my linear first pass, the overhead stuff. And then I would swap things one at a time into place and fix my heap repeatedly. Ends up there as an n log n sort. And that's n log n worst case, best case, average case. That's pretty nice. But because of the way that it works, it still ends up a little bit slower than Quicksort. Even though they have the same asymptotic complexity, the same big O of n log n, in general, the performance of Quicksort outperforms heap sort. Quicksort is a divide and conquer. We've got our average case n log n, depending on how well or poorly we pick our pivot. In terms of memory, bubble, insertion, selection, and heap sort are all in place, so we can do that with a constant amount of memory. I need just enough memory to do my swapping to make those sorts work. Quicksort needs only a constant amount of memory for the algorithm, but the implementation, the stack frames, they cause us to use some more memory. So the data still gets sorted in place, but I use more than a constant amount of additional memory because of the stack frames. How about stability? We talked about whether or not algorithms were stable, and sometimes that is important. If the output data that has the same key values remaining in the same relative locations after the sort, a 3 left of a 3 once sorted will be still left of a 3. Bubble sort and insertion sort are both stable. Selection sort was grabbing the smallest item from wherever we found it and moving it to the beginning. Not stable. Heap sort, also because of the heapifying aspect of it, was not stable. Quicksort, we know that we're swapping something from the left to the right. These broad distances, also not stable. So these are things that you want to put these some version of these last 3 slides right on your exam cheat sheet, so you can have that stuff right at your fingertips when it comes time to do this exam stuff. I've mentioned intro sort as well. This is what standard sort in the STL is based upon. So intro sort is short for introspective sort, and to be introspective is to look inside, to think about oneself. And so this is a sort that examines its own performance while it's sorting. That's how intro sort works. So here's a simple pseudocode version of intro sort. It starts out, it says, we're going to intro sort this data. Well, if the number of items is small, just use insertion sort, because, you know, insertion sort is going to be the best thing we can do for a small number of items. And that small maybe should be in quotes, because that's going to be determined by whoever writes the library. As I mentioned, I think the G++ version is 15 and below is where the insertion sort kicks in. Unimportant, but just to give you a feeling for where that is. It doesn't really go much above size 32. So if we don't have a small amount of data, let's try to do quicksort. But we realize that if quicksort is getting too deep, because we're constantly picking a bad pivot, maybe the data is forcing us into bad pivot choices over and over and over again. The more often I pick bad pivots, the more likely I am to end up as n squared. So this next branch says, if the quicksort recursion depth is too large, then we're bailing out of quicksort. We've gone too deep, it's just not going well for us. We might as well pay the price to do the overhead and keep the n log n that heap sort gives us. So if it's small, we insertion sort. If we've gone too deep in quick sorting, we're going to heap sort. Otherwise, we're going to stick to quicksort there, because quicksort does good things. So that's how intro sort works. That's what the STL sort does. You can see that you're not guaranteed stability from intro sort. If you've given it small amount of data, you jump into insertion sort, you can actually get a stable sort out of standard sort, but only if you have a small amount of data. So you really shouldn't count on that, since you don't have an idea how long that is. The heap sort, of course, and the quick sort both are not stable, so if your data gets to be too large, you're not going to get a stable sort. So there's some interesting things about intro sort there. that's our summary on sorting. We've got one more sort to see. That is the merge sort, and we'll pick that up tomorrow. As you're starting to study and put this stuff in your mind for the exam, do an illustration of the worst case input for Quicksort. There's actually quite a few different ways that I can come up with worst case input. So think about, well, if it's already sorted, that's a worst case. Yes. If it's already in reverse order, also a worst case. Yes. But there's a number of other different versions that are worst case values. So explain why the best case runtime for Quicksort is not linear. Is there a way to make it linear? Why can't we do this? Normally the pivot selection takes a constant amount of time. What happens if we sort of slow that down a little bit and take a linear amount of time? So the what happens part of that question is, how does that affect the algorithm? And you can figure out how does that affect my recurrence relation to figure out how that affects my algorithm. So improving Quicksort with linear time median selection. Can you pull that off? These are things that you can practice and study as we're moving forward. After that, we get the black screen. I somehow made it out of this lecture without everything falling down around me. Most things did, but not all of them. I'm still here, still on top. Thursday, let's get some lunch.